Welcome back, students. In this particular video we will talk about realization of full adder with NAND gates only. So we are continuing our lecture series based on universal gates implementation, and we already know what are the advantages. So we will shift our focus directly on the equation. Now as far as the full adder is concerned, we know that the sum equation we got was A XOR B XOR C. And in half adder, while we were implementing it using NAND gates, we already showed you how can we write A XOR B. So let that A XOR B equal to X. So we are again having X XOR C. And I will directly write it in the form where we solved the equation last time. So it was something like this: X dot X C in, we should write C in here, bar, then dot C in dot X C in bar, and then we'll use two bars, one here, one here. So if you don't know how this is coming, you need to go back to your half adder circuit. I will simply show you that slide today just for the reference. So students, you can see this particular slide which we have already covered, and you can see this section where we have actually solved all these steps, and the final result that we got here, that result I have directly written. So if you see this particular slide, whatever is written in this red box, that is the final equation. I have simply written it directly in my full adder. So let us go back. Now we will come to our carry equation. Now carry equation in case of full adder was something like this: A XOR B dot C in plus A dot B. So again we can write it in this format. We can write A XOR B dot C in, then we will use dot product here, then A dot B, and we will use double bar. And again the point is that both these equations are exactly same. If you will apply De Morgan in the second step, that you will again get the first step back. So they are same things. Now once we are having these two equations, we are ready for implementing all these things in a logic diagram. So let us shift to the next slide. So in order to save time, the diagram has been already implemented, but I will tell you the logic. And the second thing we have done is the two equations that we got in our previous slide, those equations also have been noted in the red box. And the logic here is we already know how did we implement half adder, and there we saw we were using 4 gates for implementation of sum, which was like for A XOR B. Now if you will realize here also, these 4 gates are actually being used to implement A XOR B, and then further other things are being used. Let that be equal to X. Now again we are using similar type of it's like we are just copy pasting this figure, gate number 1 2 3 4. It has been exactly copy pasted, and this will be X XOR C. So it is nothing but A XOR B XOR C, because X is equal to A XOR B. So that is the concept of using all these 4 gates in cascade. And the ninth gate that we are using here, that is for the carry. Now let us see step by step how all these things justify our equations. Now as far as the first 4 gates are concerned, so we said already this is X. Now what are we doing further? This X is being multiplied with C in. This is the C in input. So we get here X dot C in with bar. Now this is given as one of the inputs of gate number 6 and 7. This is X and this is C in. So what will be the output of gate 6 and 7? It will be X dot X C in bar, then whole bar, and the output of gate 7 will be C in dot X dot C in bar whole bar. So you can see the sum equation is being implemented almost. We are done with the internal steps. Now we need this extra bar, big bar. For that we are using gate number 8. So gate 8 is nothing but the dot product of term 1 that you can see here and term 2 that you can see here. So that gives us the sum, which is A XOR B XOR C. Now we will shift our focus to the carry. In carry there are two terms involved, and again if you see, let us suppose this is my term 1, this is my term 2. So let us see what are the two inputs of gate number 9. One of the inputs, as you can see very clearly, is x into C in bar, and x is A XOR B, so it means this is giving us term 1, means C in dot A XOR B whole bar, and term 2 is coming from this particular output. And what was this output? It was A dot B with bar. So this line is A dot B with bar, that is term number 2. That is what T2 is. And ultimately we are doing NAND operation which will implement this bar. So carry equation is being implemented here. So again there is one important point here for your competitive exams. If they ask you how many number of NAND gates are required to implement full adder, the answer would be 9. So 9 for full adder and 5 for half adder. So that's it for today. As far as the last possibility is there, that is realization of full adder with NOR gates, I would request you that you should try it by yourself. So I will then shift my focus to subtractors in the next video. So till then, keep revising. In case you are having any doubts, do ask in the comment section. I'll see you in the next class. God bless you all and have a nice day.